Amol sir.
Yes.
हे लाईव्ह केलेलं आहे, आपण करू शकतो आता.
Okay. Sharma sir.
Yeah, Amonji. Yeah.
We can start now.
Okay.
Yeah.
Okay. Good afternoon to you all. Due to unforeseen that situation in the morning, we have to break. Now we'll continue with what we have started. We have completed this modified ranking. Is it okay?
Yes, sir.
Hello.
Yes, sir.
Okay.
Yes.
I'm morning we were gone about the power plant cycle. So this water and steam cycle, the water from this condenser, it is pumped by means of condensate extraction pump, then the boiler feed pump, it goes to the boiler, and from boiler through various superheaters. First in the drum, the separation of water and steam takes place. The water again goes to the water wall in the boiler, and the saturated steam from the drum, it goes to the superheater, that LTSH, PSH, Platon superheater, and final superheater. And this main steam, this terminology I'm showing here, that will be used in the heat rate calculation for that purpose. The outlet of the final superheater from the boiler is called as the main steam. You can see FSH. After FSH, the parameter is 155 kg and 540. It goes to the HP turbine. Then the exhaust of the HP turbine, it is CRH, that is cold reheat. It goes to the reheater in the boiler. And after reheating, it is known as HRH, hot reheat. Its temperature increases. It's 37 kg and 540 degrees centigrade at the IP turbine inlet. Then the exhaust of IP turbine, it goes to the LP turbine and then to the condenser. So this is the whole water and steam cycle. Now this air and flue gas cycle, as you were told in the morning, this pulverization of the coal takes place by means of the coal mill. This is here in different types of power plant, different types of mill are there. So at our location, it is ball and tube mill, where the steel balls are used inside and there are liners on the shell. So what happens when the shell rotates, the raw coal which is coming in the coal mill, it gets crushed by means after coming in contact with the steel balls and the liners. So this crushed coal, it comes in the pulverized form, and the PA fan, that is primary air fan, the hot PA air, this carries the pulverized coal from the coal mill to the boiler, and the firing takes place. And there are FD fan, 2 FD fan and 2 PA fan. PA fan carries the coal, and this FD fan, it provides the excess air for complete combustion of the coal inside the boiler. So this is the FD fan, it is providing the secondary air to the furnace. And after combustion, the flue gas from the boiler, after first pass, then horizontal, giving heat to the superheaters and then to the economizer, and the flue gas comes to the air preheater, where the remaining heat in the flue gas is given to the surrounding air, incoming primary and secondary air. Then after air preheater, the flue gas goes to the ESP, electrostatic precipitator. This is for removal of ash content inside the flue gas. This ESP is the main function. Then this ID fan, it sucks the flue gas from the furnace and it maintains the draft. Now since both ID and FD fans are there in the system, so it's a balanced draft type of system. So slightly negative furnace pressure is maintained around minus 10 to 15 mm of water column. And at the exhaust of discharge of ID fan, we have installed the FGD for removal of the sulfur oxides from the flue gas. And then the clean flue gas is sent to atmosphere through chimney. So this is the whole air and flue gas cycle. Now this is the complete cycle. You can see the primary air fan and FD fan. This pulverized coal is supplied to the boiler. This is the boiler structure. And the flue gas from the boiler, it goes to air preheater, ESP, and then to chimney. And the steam from the superheater, it goes to HP turbine, then IP, then LP, and from condenser, the condensate extraction pump pumps the condensate to the deaerator. This deaerator is a storage tank for the BFP, boiler feed pump. So considering our unit, this boiler feed pump, it's the major power consumption consuming auxiliary. Out of 250 megawatt we are generating in unit, the 9 megawatt is consumed by means of this pump. It's a high pressure pump to pump the feed water to the boiler. And in the condenser, since we are located near the sea, so we are using the seawater for condensation of the steam from the LP turbine in the condenser. So we are utilizing the seawater and condensing the steam from the LP turbine. So there are other power plants which are not located near the sea. They are using the fresh sweet water. So their cooling tower is there for cooling that cooling water. And the generator, it is directly coupled on the main shaft of the turbine. So depending on the capacity of the unit, the turbines are there. If the unit capacity is less, then only one turbine will be there. If high, then 2 or maybe maximum 3. So here we are having HP, IP and LP turbine. These are directly coupled to the generator. Okay, am I audible? Hello? Yeah, Amol sir? Hello?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Yeah. These are the, now we have seen the complete cycle. The cycle efficiency, can anyone tell what is the cycle efficiency of any thermal power plant? Hello? Hello?
It's between 35 to 40%.
Yeah, yes, correct. It depends on the capacity and also. So normally there are two types of boilers, subcritical and supercritical. So less capacity unit below around 600 megawatt unit, they are having the subcritical boiler, and the units having more than capacity 600 megawatt, they are having supercritical boiler. And the difference between subcritical and supercritical boiler is the operating pressure. So the critical point is around, what is the critical point? Critical pressure, it is 221 bar. So all the power plants operating at less pressure, lesser than 221 bar, they are having the subcritical boiler. And if they are operating more than 221 bar, then it's supercritical boiler. So this is the various, this figure shows the various energy losses in the power plant. So if we consider the 100% fuel input, then 11% losses around roughly takes place in the boiler. The boiler efficiency is between 85 to 90%. So around 11 are losses in the boiler. Then the cycle efficiency, maximum 44.7%, these losses are there in the condenser, where the condensation of the steam takes place. So we are taking the heat from the steam. So in the condenser, this is maximum heat loss is taking place. Then in turbo generator, around 5 to 8%, average we are consider here 6%. Then various station auxiliaries. So the net electric output is 36%, and the cycle efficiency is here 38%. So if supercritical boiler is there, then the cycle efficiency is in between 38 to 40%. If it is subcritical boiler, in that case 35 to 37%. Now these are the some performance terms used in the power plant. The heat rate. The heat rate is the opposite of the efficiency. So the efficiency is for calculation of efficiency of any auxiliary or any cycle. Efficiency is output upon input, but heat rate is opposite of the efficiency. It is input upon output. So if for calculation of the heat rate for the thermal power plant, input upon output, the input is coal. Suppose if we are considering the coal based thermal power plant, so the input energy is the coal, so and output is the electricity what we are generating. So the heat rate is the cycle efficiency, it is opposite. It is the heat required to produce 1 unit shaft output, means heat required to generate 1 kilowatt hour of electricity. So its measurement is kilocalorie per kilowatt hour. So it is input upon output. So kilocalorie is heat input through, suppose we are burning coal, then how much kilocalorie heat is input by the coal burning, and divided by kilowatt hour, means how much output we have generated by means of the generation. So kilowatt hour. So the unit of heat rate is kilocal per kilowatt hour. And PLF, it is, as the name suggests, plant load factor. It is actual generation upon generation at design install capacity, means how much we have generated actually, and design divided by design generation. It is plant load factor, means how much the unit is loaded. Then availability is time period of the machine unavailability divided by total period considered, means how much time throughout the day the machine is available or unit is available. Then loading factor is PLF into 100 upon, means within the available time how much the unit is loaded, that is loading factor. and partial loading is 100 minus loading factor. And specific coal means amount of coal required to generate 1 kilowatt hour of output. So its unit is kg per kilowatt hour. Okay. So if you multiply this specific coal by GCV, that is gross calorific value of the coal, then we'll get the heat rate directly. So these are the some performance terms used in the power plant. And this is the overview of all plant efficiency and heat rate. So in this figure, if we consider, so we are burning the coal in the boiler, then from boiler we are generating the steam, it is going to turbo generator, and finally the output is there. So if we consider the input of 120.7 tons per hour of coal of having GCV 4000 kilocal per kg. So heat input by burning the coal is 482.8 million kilocal per hour. So this is heat input. And for boiler process, if we consider the steam generated, so that is considering the boiler efficiency 87%, so we can generate 420 million kilocal per hour. So this is the boiler efficiency, output of boiler divided by the heat input in the boiler by burning the coal. Then the steam from the boiler, it goes to the turbine and it generates the electricity by the generator. So the output of the generator divided by the turbine, it is turbine heat rate. So it is 2000, if you can consider kilocal per kilowatt hour. And this is the final output after consuming the auxiliary power consumption. So if we consider the net output and gross input, then we can get the net unit heat rate. So this is the boiler efficiency, and if we consider the only turbine input and output, then it's TG heat rate is calculated. Then TG heat rate divided by boiler efficiency is gross unit heat rate, and gross unit heat rate divided by the auxiliary power consumption, then you can get the net unit heat rate. So these are the various terminology for plant efficiency and heat rate calculation. Now turbine audit. So as we have seen, thermal power plant is one of the designated consumer. So as per the AC Act 2001, it is mandatory to conduct energy audit, and energy audit involves the audit of various auxiliaries and equipment. So one is the major is turbine audit, and then the boiler audit, then various other auxiliaries, condenser, BFP, cooling water pump. So what are the steps involved in the turbine audit and how the performance is calculated, that we'll see now. So these are the steps involved in conducting any energy audit. So the steps involved in conducting an energy audit of the turbine are, first one is the data collection. Suppose we want to conduct the turbine audit, means we want to calculate the performance of the turbine. So the main performance factor we have seen for turbine is the TG heat rate and turbine efficiency. So for that purpose, the first important step is the data collection. Then after collecting the data, so we have to collect the data for depending on the period, 1 day or 2 days, that accordingly we can decide and collect the data. Then we have to do the observation and analysis. So as per the calculation sheet, we have to calculate all the performance factor, and by observing the data, previous data, and compare it with the design data, then we have to see the deviations, which factor has affected, which losses are increased, that we have to see. And then finally, after that, exploration for energy conservation measures. Then we have to also see some energy conservation measures can be done or not. And finally is the report preparation. So these are the steps involved in conducting any energy audit. So specifically, we'll be seeing now for turbine audit. Now for energy audit, some instruments are required for parameters and measurement. The following instruments are normally required for turbine audit: temperature indicator and probes for measuring the temperature in the various process entity, that is for steam, air, and like that. Then pressure gauges for measuring the pressure. Then flow measuring instrument for steam and water flow measurement. Then ultrasonic leak detector, because in the power cycle, in the various processes, there are so many valves, and if these walls are passing, if these walls then that loss will be there. So this ultrasonic leak detector is used to get the any wall deviation is there, defect is there, or if it is passing. So for that purpose, ultrasonic leak detector is used. So while conducting the turbine efficiency test, and measurement of steam flow, pressure, and temperatures are very essential. The main important parameter that has to be measured for in the turbine audit for turbine efficiency and heat rate calculation is the main steam flow, which is input to the turbine. So the steam is generated from the boiler and finally it goes to the turbine. So this is the critical parameter to be observed. So for that purpose, the correctness of the instrument, its calibration is required. And for any audit, and specifically turbine audit, calibrated online instrument can also be used for conducting the test. Normally, if the auditor comes from, we have hired an external agency, then they will bring their own instrument. But if we are having our own calibrated instrument, that can also be used for the audit purpose. Now, first we'll see how the turbine efficiency is calculated and what are the parameters are required. As we all know that the turbine efficiency is the for individual, because we have seen depending on the type of the unit, turbine HP, IP, LP, 1, 2 or 3 turbines are there. So cylinder efficiency is to be calculated. To measure how well a turbine is performing, we can look at its isentropic efficiency. For turbine efficiency, we can also call it as isentropic efficiency or cylinder efficiency. This compares the actual performance of the turbine with the performance that would be achieved by an ideal isentropic turbine. When calculating this efficiency, heat loss to the surrounding is assumed to be 0. So here the heat loss is considered 0. So we can calculate the cylinder efficiency by actual enthalpy drop upon isentropic enthalpy drop. So this is the main formula for calculation of the turbine efficiency. So for efficiency calculation, these are the parameters to be measured. Suppose we are carrying out a performance test for 4 hours. So normally it is performance test is carried out for 4 hours, and this 4 hours continuous data is taken and the efficiency is calculated. So these are the parameters are to be measured. First one is the MS pressure before ESV, that is main steam pressure before this. ESV means emergency stop valve, before the stop valve of the turbine. Then main steam temperature before ESV. Then HPT exhaust pressure. Suppose we are calculating the efficiency for HP turbine, then it's exhaust pressure and exhaust temperature. Means inlet pressure, inlet temperature, then outlet pressure, outlet temperature. Similarly, this is HRH steam pressure before IP turbine valve and HRH steam temperature. This is for IP turbine. Then IP exhaust steam pressure and temperature. So for turbine efficiency, we need the parameter for inlet and outlet of the turbine. So before are the inlet parameter, then and this pressure and temperature is required for calculating the enthalpy, because as from steam table, if we get the main steam pressure and temperature, then we can calculate the enthalpy. And this is the diagram showing the turbine cycle measurement points. Normally these points are predefined, and their temperature indicator, thermocouple and pressure transmitters are already fitted, so we can directly get these values, or we can use the offline instrument also for measuring this. So this is the main steam line. This we can see. This is the inlet of HP turbine, and this is the exhaust. So this is the MS pressure and temperature, and this is CRH, cold rain. The exhaust of the HP turbine is CRH, cold rate line. So this is the HP exhaust pressure and temperature. Similarly, this is IP turbine. IP turbine inlet is hot rate steam, HRH. So this inlet pressure and temperature, and this is the exhaust parameter of the IP turbine. It goes to the LP. Now, how we can calculate the turbine stage efficiency? So this is the HS diagram. This H point, capital H, is the, suppose if we consider this diagram for the HP turbine, this H point is the operating inlet parameter for the HP turbine. And suppose this is horizontal line is the entropy, and vertical is the y-axis is the enthalpy, and x-axis is the entropy. So this HX, X capital, this is the isentropic expansion. If we consider there are no losses in the system, but due to losses and all this, the actual expansion of the steam which is taking place in the turbine, it deviates from X to Z. So for calculating the turbine stage efficiency for any turbine, HP, IP or LP, so the heat drop, actual heat drop will be HZ, and isentropic heat drop will be HX. So the enthalpy at point H and enthalpy at point Z and enthalpy at point X, we need to calculate from the steam table by the inlet and outlet pressure and temperature, and we have to carry out this turbine, calculate this turbine step efficiency by this formula. So this is the formula: turbine efficiency is used energy divided by available energy, means enthalpy at inlet minus enthalpy at outlet divided by enthalpy at inlet minus isentropic enthalpy, considering the isentropic expansion. So by this way we can calculate the turbine efficiency for HP turbine, IP turbine and LP turbine. Now the second important parameter is the heat rate. So the heat rate we can calculate for turbine heat rate. Then for whole unit, that is unit heat rate, by calculating the turbine heat rate and dividing it by boiler efficiency, we'll get the unit heat rate. And if we consider the net output, that is by after subtracting the all auxiliary power consumption, then we'll get the net unit heat rate. And inverse of the heat rate is the efficiency. Now for heat rate, these are the parameters are to be measured for heat rate calculation. So similarly, same, all turbine inlet and outlet pressure temperature, that is MS pressure, MS temperature, HP turbine exhaust pressure temperature, IP turbine inlet pressure temperature, then also feed water pressure and temperature going to the boiler, then all extractions. There is a in modified Rankine cycle, this regenerative heating is used to improve the efficiency of the overall power plant cycle. So for this, the heaters are used in the cycle. So these heaters, it is known as the regenerative feed heating, where some part of the steam is taken and it is used for heating the incoming feed water and condensate going to the boiler. So if we send the water to the boiler at higher temperature, in that case what will happen? Our coal consumption in the boiler will be lesser, so finally it will increase the efficiency. And if our coal consumption is less, means output upon input, if input is less, in that case the efficiency of boiler and all plant efficiency will be more. So this heater performance also we have to calculate. For that purpose these parameters are required. Then feed water temperature, means how much the feed water temperature gain is there in the heaters, feed water pressure and temperature. Then this is the main steam flow. This is the important parameter for calculation of the heat rate and feed water flow. Then reheat flow, superheater and reheater spray. Normally these spray are required for maintaining the temperature at the outlet of the boiler near to the design temperature. If the temperature are less, then the efficiency will be less. And if it is on the more side, higher side, then it will affect the metallurgy of the boiler and other parts. And also the spray which is there to maintain the temperature, it is also increasing the loss, means. So for that purpose, this spray should be as minimum as possible. So these are the parameters need to be measured for calculation of the heat rate. And from all these parameters, these enthalpies has to be calculated from the steam table. So enthalpy of main steam, then enthalpy of CRH, HRH, feed water enthalpy, superheater spray enthalpy, reheat spray enthalpy. Then all these enthalpy has to be calculated based on the previous parameters from the steam table. Now heat rate, as I explained earlier, this is the common term used to reflect the efficiency of power generation plant. It is the heat input in kilocal or kilojoule for generating 1 kilowatt hour of electrical output. So it is opposite of the efficiency. So efficiency is higher is better. Similarly, the heat rate, if it is on lower side, then it will be better. So in India, coal-based power plant overall efficiency ranges from 28 to 35%, and heat rate is heat input in kilocal upon power output. 1 kilowatt hour of electricity is 860. So we can directly calculate the unit efficiency from this heat rate by multiplying it by 860. Now heat rate, as I explained in that diagram, there are two: gross unit heat rate and net unit heat rate. The difference is gross heat rate, it considers the gross output, and net unit heat rate, it considers the net output. Means for output we have to supply the auxiliary power consumption, and auxiliary power consumption is the power consumption required for all the drives which are running in the power plant generation of electricity cycle. So normally the average auxiliary power consumption for any unit is in the range of 8 to 10%. Suppose if we consider the 10% auxiliary power consumption, in that case, suppose if we consider our unit is 250 megawatt design. So if we consider the 10% auxiliary power consumption, then 25 megawatt is used for the auxiliaries which are running for the power plant cycle for generation of electricity. So our net output is 225 megawatt only. Okay. Hello. Hello.
Yes,
Hello.
sir.
Yeah. Okay.
Yes. Yes, sir.
Then these are the some of the thumb rules or some parameters, that is impact of turbine efficiency on heat rate. So 1% HP turbine efficiency, its effect on heat rate is 0.16% and effect on output is 0.3%. Then efficiency of IP turbine, 1% deviation, it changes the heat rate by 0.16 and output by 0.3%. And LP turbine, its impact is much more. It is 0.5% on the heat rate and 0.5% on the output. And if we consider the three cylinders, HP, IP, and LP turbine, the output sharing, this is given for 210 and 500 megawatt unit. For 500 megawatt, HP turbine output is 27%, IP is 34%, and LP is maximum 39%. So these are the percentage output sharing by individual turbine. Now we have seen all the parameters to be monitored, and from that steam table we have to calculate the enthalpy. Now for heat rate calculation, we have to use this formula for gross turbine heat rate calculation for turbine heat rate. For turbine heat rate is for heat rate, it is input upon output. So if you consider for turbine, the input is the steam flow and output is the megawatt generated. So input steam is for HP turbine, it is main steam flow into main steam enthalpy minus eco inlet, that is feed water enthalpy. So this is for HP turbine. Then for IP and LP, it is reheat flow into HRH enthalpy minus CRH enthalpy. So this is the by this formula we can calculate the turbine heat rate divided by megawatt generated. Then gross unit heat rate we can calculate from gross turbine heat rate by dividing it by boiler efficiency. So by this formula we can calculate the gross unit heat rate. Then for net unit heat rate, same turbine heat rate divided by, we have to consider the gross net megawatt here, means megawatt generated minus auxiliary power consumption. Suppose I have given the example for our 250 megawatt unit, the output for turbine heat rate we have to consider, or gross unit rate we have to consider 250 megawatt, and for net turbine or net unit heat rate we have to consider the output 225 megawatt. Means we have to subtract the auxiliary power consumption for calculating the net turbine or net unit heat rate. Okay, so from this net turbine heat rate we can calculate the net unit heat rate by net turbine heat rate divided by boiler efficiency. Okay, now how we can improve the heat rate? This in the audit we have calculated the heat rate. Now we have to check the previous performance and PG test data and compare which turbine efficiency has changed or heat rate how much deviated. Now heat rate depends on various factors which are during operation. We have to check all these parameters and if any deviation is there in this parameter, then heat rate is affected. So these are the various parameters involved in the cycle, so on which the heat rate depends. So heat rate depends on unburnt carbon. Suppose if you are considering the coal-based thermal power plant, if the unburnt carbon is more, then the heat rate is more, so it is affecting the heat rate. Then exit flue gas temperature, then condenser back pressure, DM makeup, and reheat pressure drop. So all these parameters should be on lower side. In that case, better will be the heat rate. So unburnt carbon, if it is more, then heat rate is increasing. Exit flue gas temperature should be less, condenser back pressure should be less, DM makeup should be less, and reheat pressure drop should be less for better heat rate. And these are the parameters has to be on higher side or on maximum side for better heat rate, that is main steam pressure, feed water temperature, and main steam and reheat temperature. If these parameters are on higher side, then better will be the heat rate. So for heat rate improvement, for maintaining the heat rate or for improving the heat rate, we have to control all these parameters. Now, how we can control these parameters, we'll see one by one. And this is the impact of all these parameters on the heat rate. So you can see the main steam temperature, if it is deviation by -5 degrees centigrade, then heat rate will increase by 2.3 kilocal per kilowatt hour. These are the some of the thumb rules, and it differs with the different power plant, but this is the general average value. So, and this deviation is compared with respect to the design value. Suppose the main steam temperature, if you can consider all the units, their design main steam temperature and reheat temperature is around 537 degrees centigrade. So we have to maintain this parameter near to the design value. So if any parameter deviates from the design value, it is directly affecting the turbine efficiency and heat rate, and finally the unit efficiency. And also the main steam pressure, if it is deviated by 1 kg, then effect on heat rate is directly 1 kilocal per kilowatt hour. Reheat temperature by 5 degrees centigrade affect the heat rate by 2.3. Reheat spray, if any 1% flow is the reheat spray valve opens, then it affect the heat rate by around 2.4 to 3.6. Then condenser back pressure 1 mmFg, then it is affecting the heat rate by 2 kilocal per kilowatt hour. And feed water temperature at the inlet of boiler, if it is lesser by 1 degree centigrade, then it increases the heat rate by 3.5 kilocal per kilowatt hour. So these are the factors which are affecting the heat rate and their deviation, how the heat rate is affecting. And the main performing equipment or is the condenser. The condenser performance plays a vital role in cycle efficiency. So if the condenser performance is not good, in that case, we will not get the condenser back pressure. So if the condenser back pressure is more, then more steam flow or more coal consumption is required for the same output. And for considering the economical impact, any performance parameter will not come to know its criticality or severity if you don't compare it with the economical figure. Then this is the roughly calculated value for the one heat rate loss for 1 kilocal per kilowatt hour, considering the GC of 3700 kilocal per kg and coal price of 4400. So in that case, loss in heat rate by 1 kilocal per kilowatt hour, it comes around rupees 47 lakhs. So we can see how much these parameters maintaining plays a vital role for maintaining the heat rate. So change in heat rate by 1 kilocal per kilowatt hour will have a loss of around 47 lakhs. Now these are the all controllable losses. So for heat rate maintenance, means if you want to maintain the heat rate, this we can maintain all these parameters during our normal day-to-day operation: main steam temperature, main steam pressure, reheat pressure, feed water temperature, condenser back pressure, then superheat and reheat flow, then boiler exit gas O2 and temperature, boiler efficiency and HPIP efficiency from these values is calculated, and loss due to passing of high energy drain wall. Suppose any drain wall, it is open to atmosphere, and if in closed condition it is passing, then in that case this high energy steam or water is lost to the atmosphere. So that is directly a loss. So it is affecting the finally efficiency or heat rate. Now for main steam pressure at turbine inlet, how we can control, what is its effect, that we'll see. A change in turbine stop valve pressure will result in corresponding output. If main steam pressure at the turbine inlet, if it is on the lesser side of the design value, means the heat input for any, it depends on the operating pressure and temperature. If the pressure is less, in that case heat input is the less, enthalpy will be less. So more steam flow is required and heat rate will increase or efficiency will reduce. So we have to maintain the main steam pressure at rated value or up to the higher value. So if main steam pressure is on lesser side, then effect of change in main steam pressure, the steam flow will change, and change steam flow will cause the pressure through the turbine to change, including bleed steam pressure. And because of this, the feed water outlet temperature also will change, and total heat of the steam and reed steam and final feed water flow will change, and boiler feed pump output will change to cope up with the change flow. So if any single main steam pressure is reduced, then all these parameters will be affected, and finally the turbine efficiency and turbine heat rate will change. Now main steam temperature, because what happened during normal operation, during different types of coal firing, and the temperature and pressure changes. So the operator's main job is to maintain the pressure and temperature near to the design value. So if temperature changes, the variation in the steam temperature result in variation in specific volume of the steam and results in change of steam flow. As I said, the enthalpy depends on the pressure and temperature. So what effect is taking place due to main steam pressure, the same effect will take due for main steam temperature. If the temperature is on lesser side, then the flow required to generate the same output will be more. So its effect are change in total heat of steam, then change in total heat to HP cylinder exhaust steam, and change of flow will alter the pressure throughout the turbine, and this will change the bleed steam flow to heaters. So this is the effect taking place due to change in main steam temperature. Now similarly, main steam pressure and main steam temperature affect the HP turbine efficiency and heat rate also. Similarly, reheat pressure and reheat temperature affect the IP turbine efficiency. The variation in reheater outlet steam temperature will cause change in total heat of the steam and a change in steam flow to condenser for given loading. So this is the standard or thumb rule for change any in main steam pressure, main steam and reheat temperature. So we have seen earlier same 1 kC and 1 degree it affect the heat rate by this value 1.5, and deviation in heat rate by 1 kilocal per kilowatt hour will incur a loss of around rupees 50 lakhs. Now this we have seen about the turbine performance, turbine efficiency and turbine heat rate calculation. Then heater performance in a turbine cycle, there are various heaters depending on the capacity of the unit. LP heaters, HP heaters. These HP heaters are mounted on the feed water side and LP heaters are mounted on the condensate side. So these heaters are the efficiency improvement device. This is also known as regenerative feed heating. So where some part of steam from the turbine is taken and it is given in the heater on the shell side, and on the tube side the condensate or feed water is passing. So by the incoming steam, the inlet temperature, outlet temperature of the heater increases, and finally the feed water which is going to the boiler, its temperature increases by the use of the heater. So if any water which is going to the boiler, its temperature is more, then less coal consumption is required. So it is directly improving the efficiency of the boiler as well as turbine. Now similarly for heaters, this HP heater and LP heater, for calculation of their performance, these parameters need to be taken. These are the parameters required to be collected for checking the performance of the heaters. So its parameters required are feed water at the inlet and outlet pressure and temperature, then its extraction steam pressure and temperature, and its drain temperature. So all these parameters needs to be calculated, needs to be taken, and from that values we have to calculate this various performance parameters of the heaters. The performance of the feed heat water heaters can be analyzed by monitoring this terminal temperature difference, that is known as TTD, then drain cooler approach, that is known as DCA, and the pressure drop on the feed water side. So by getting all these parameters of heaters, we have to calculate this TTD and DCA and delta T across the heaters. So now how we can calculate this TTD and DCA? The terminal temperature difference, it is calculated by T saturation minus T feed water outlet. So we can calculate the TTD for individual heater by T saturation minus temperature at the outlet. Suppose if we consider the any HP heater, so T saturation means the saturation temperature taken at the heater cell pressure, means it is the saturation temperature of the steam which is taken as a extraction. Suppose any heater, the extraction steam pressure is 10 kg. So at 10 kg, what is the saturation temperature that we have to calculate? And water side outlet temperature. This is T feed water outlet. So this is calculated, TTD is calculated by Tsat minus feed water outlet temperature. Similarly, drain cooler outlet temperature we can calculate T of drain minus T of feed water inlet temperature. Means temperature of drain means the drain which is leaving the heater, that is T drain minus feed water inlet temperature. So we can calculate DCA by this temperature of the drain and temperature of the feed water entering the heater. And third one is the temperature rise. How much temperature rise of feed water or condensate taking place in the heater. So we have to calculate all these three performance parameters for the heaters, and we have to compare these parameters with the PG test value or design value or last performance. And if any deviation is observed, then we have to analyze why this deviation is there, whether the performance of heater has deteriorated, any scaling is there, and then what action have to be done accordingly. Then we have to do that actions. Now these are the various feed water heater reasons for performance deterioration. The deterioration of feed water heater performance occurs for the following cause. One is the air accumulation. If any air charging is not there, proper charging of the heater is not there, in that case the heat transfer will not be there. The heaters are the major are the heat exchanging device, heat transfer device only. Say they transfer the heat from the steam to the feed waters. So if while charging, the proper charging care is not taken, then air accumulation may take place, so it affects the performance. Then steam side falling. So on the steam side, on the tube, if any deposition is there, then it will affect the heat transfer. Then water side falling, because in the heaters on the tube side the water is going, and on the shell side the steam is there, extraction steam. So if water side on the tube side falling is there, then in that case also the heat transfer will not be there. Then drainage effect, if any drainage is choke, proper flow is not there, in that case also the feed water performance will get deteriorated. So by observing all these performance parameters, that is TTD, DCA and temperature rise, we have to see which parameter is affected, and accordingly we have to carry out the overhauling or servicing of the heater. Then these are the some of the problems that can occur with the heater, that is tube puncture due to corrosion or selection of wrong material. Normally this is one of the major problem is normally taking place in the power plant regarding the heaters, because most of the time if proper charging is not taken, in that case the tube may get punctured. So this has to be rectified during the opportunity, because we can't stop for that. So temporarily it can be plugged, this tube can be plugged by identifying the correct tube, and we can start the heater also, we can take it in service. Then parting plate leakage because what happens when the in heater the inlet feed water and in between the inlet and outlet feed water there is a parting plate. If this parting plate get ruptured, in that case the bypassing of the heater may take place, means directly the inlet feed water get mixed with the outlet at high temperature outlet feed water, so it will affect the performance of the heater. Then joint leakage, water side falling and drainage effect, these are the some of the problems that may occur with the heater. So if air accumulation occurs, it is manifested in the following: reduce heater drain water temperature, increase TTD, and reduce temperature rise of the feed water to condensate. So if air accumulation takes place, then it will affect the performance by increasing TTD, and temperature rise will be reduced. Then if steam side falling is there, in that case also will not get the performance of the heater, our feed water temperature will not rise, then in TTD will increase. And if water side falling is there, in that case also the feed water temperature rise will not be there, and thermal magnification of the trouble are similar to steam side falling. So this is the impact of feed water performance on heat rate. If any feed water outlet temperature is changed by 1 degree, means feed water outlet temperature of heater, means the same temperature feed water is going to the boiler. So at the boiler inlet, if the feed water temperature is reduced by 1 degree centigrade, then heat rate will increase by 0.78 kcal per kilowatt hour. This is the thumb rule. Now, as I said, the condenser performance plays a vital role in the overall unit cycle efficiency as well as turbine efficiency or turbine heat rate. So we have to maintain the condenser performance up to the mark. So for this, these are the various factors which are affecting the performance of the condenser. Condenser is one of the heat exchanger device. It is condensing the exhaust steam of the LP turbine, and this condensate is again then pumped back to the boiler. So in the condenser, we are using the cooling water for condensing the LP exhaust steam. So variation of CW inlet temperature will affect the condenser performance. If the CW inlet temperature is more, in that case condensation will not be there proper. In that case back pressure will also increase. So if back pressure increase, then more steam flow is required to generate the same output. Also, since in condenser back pressure or negative pressure is maintained, so there are chances of air ingress. If air ingress is there, then proper heat transfer will not be there. So we have to maintain the vacuum, that is back pressure, at design level. Then in condenser also, the cooling water passes through the tube, and on the shell side LP exhaust steam is there. So falling of condenser tube, scale formation also affect the performance of the condenser. Then deterioration of vacuum pump. So in the condenser also, the vacuum pump is sucking the all non-condensable gases. So if the deterioration of vacuum pump is there, then proper back pressure is not maintained. And also if the reduced cooling water flow, if the flow is reduced due to the CW pump performance, in that case also will not get the proper back pressure. The back pressure will increase. And high heat load, because there are so many drains of main steam line, cold reheat line, hot reheat line. These are connected to the condenser. So if these drains are passing, means continuously they are feeding the high temperature steam to the condenser. In that case, the heat load of the condenser will unnecessarily increase. So will not get the back pressure, and if back pressure will increase, so the turbine heat rate will increase. So these are the factors affecting the condenser performance. And this is the impact of condenser vacuum, that is condenser back pressure, on the heat rate. So major impact of condenser vacuum is there on the heat rate. So at various levels, if the condenser, normally condenser back pressure, that is condenser vacuum, is maintained on the negative side. So normal value, if we consider for our unit, is -0.92. So at lower vacuum level, the drop in the change in the heat rate is much more. If the vacuum drop from -0.88 to -0.90, in that case the change in heat rate is 13.2, and for 9.4 to 9.5, -9.4 to 9.5, it is 3.90. So this is the impact of condenser vacuum on the heat rate. Now one of the important parameter is the makeup water. As we have seen, our this water and steam cycle, it's a closed cycle. Only the water, we have to do the makeup for all the evaporation loss and the leakages only. Suppose if we consider 250 megawatt unit, the steam flow required is around 750 tons per hour. So this 750 tons per hour of steam and water flow, it's a close, so it's continuously in circulation. And if any leakages and evaporation losses are there, that we have to cope up with the makeup. And every power plant is designed for some makeup. So our plant is designed for 3% makeup, but we are operating at around 0.2, 0.3%. So if the makeup is on lower side, in that case heat rate will be better. If the makeup water consumption is more, then heat rate will be higher. So makeup water is replacing the water and steam which is lost from system and contains considerable quantities of heat. There are 4 usual sources of loss. So this makeup water increases due to passing of walls. Suppose any wall is there and it is leaking to the atmosphere, so unnecessary heat is lost, and we have to do the makeup for this loss. Then boiler blowdown also increases the makeup water consumption. Then drain going to waste also increases, and soot blowing also increases the makeup water consumption. This why soot blowing is important, that we'll see in the boiler audit. Now these are the some of the best practices that can be done for DM water reduction. These are monitoring of DM water consumption in a shift. Suppose regular DM water consumption is monitored, then we'll come to know whether the DM consumption is increased or not. Then monitoring of soot blowing drain wall passing, monitoring of passing of safety walls and drain walls. Then special teams may be formed for identifying, reporting the DM. Then attending a water and steam leakage as early as possible. Because what happened, the power plant is continuously running 24/7. So if any leakages is on higher side, in that case, if it is not possible to attend, then we have to stop the unit, and it's not feasible. So we have to try whether this leakage can be attended online, and try to attend it as early as possible. If the leakage persists, in that case, the makeup water consumption will be more, and it is affecting the efficiency as well as heat rate. This is the total summary of all the parameters on boiler efficiency and heat rate that we have seen. Turbine side parameters in between time to time. This main steam pressure, main steam temperature, feed water outlet temperature, DM makeup, MS flow, and condenser vacuum, and its effect on heat rate. And similarly, these 1 to 11 parameters are of the boiler side. So their effect on the boiler efficiency, and finally the heat rate. This is there. We'll see in the boiler audit also these parameters. Now I'll go with for some of the best practices what we are adopting, and also other power plants should adopt for the heat rate improvement. First one is the this is important, and we know that anything what we want to improve, if we don't monitor and if we don't analyze, then we can't improve. So for that purpose, daily heat rate deviation monitoring is there in daily plant meeting. So, and why this deviation is there, then we are analyzing and acting on that. Then heat rate deviation discussed based on weekly average in daily planning meeting, and review of action plan for major deviation. Then also we are using the software package for real-time performance analysis and efficiency optimization. So as we have seen in turbine audit, this how turbine efficiency and heat rate is calculated. So we have an online software, because all these parameters are coming from the process only, main steam pressure, main steam temperature, and we are monitoring it online on a regular basis. So we have a software system which is directly taking all these parameters, and we have inbuilt a steam table also. So from that this performance package is there, so it is directly calculating the heat rate and turbine efficiency on real-time basis. So we can come to know this efficiency and heat rate on real-time basis. Then merit order operation of the unit means we have 2 units, and any unit whose heat rate is better, so we are loading that unit more. So that philosophy we are adopting. Then continuous online monitoring of combustion parameters, because this is also affecting the heat rate. Then proper closing and sealing of manholes in the boiler. Then optimization of tapering air to mill, that we'll see in the afternoon for boiler audit. Then mill outlet. Then trending of superheater and reheat spray levels. So this superheater and reheat spray, we are optimizing it, we are reducing and trying to keeping it at minimum as possible, because it is directly affecting the heat rate. Then auto operation of burner tilt to control the reheat spray and reheat temperature. Then regular monitoring of condenser vacuum and backwashing as per the requirement, and monitoring of condenser performance by online kinetometer. So condenser vacuum we are monitoring and carrying out the backwashing for steams tube side falling if is any. Then condenser pass cleaning by load reduction on available opportunities. So if any condenser side vacuum deterioration we observe, and in that case there are 2 condenser passes are there. So during night hours, during low load, we are isolating the condenser pass and carrying out the maintenance activity if it is required. Then cooling tower field cleaning. So here we are using the seawater for condenser cooling, but where other power plants are there where the seawater is not there, in that case they are using the fresh water, that is sweet water, and cooling tower is there for the for this sweet water temperature reduction. So that cooling tower fill cleaning has to be carried out regularly to avoid the choking of the condenser tube. Then monitoring of CEP gland seal water and supplying only from CEP discharge header. So this is reducing the DM water consumption. Then regular checking of air ingress to condenser by monitoring vacuum pump discharge quantity. So in vacuum pump, there is a rotameter which directly shows the air ingress, and by monitoring that, we can come to know the air ingress in the condenser if increase or not. Then arresting air ingress point of condenser through physical inspection and helium leak detection test. Also, before the shutdown of the unit or normal running, we are carrying out this helium leak detection test to identify the points of the air ingress in the condenser and attending it on priority, because condenser performance plays a vital role in heat rate improvement. Then monitoring of vacuum pump performance. Then optimize operation of on-load tube cleaning system. So we have this on-load tube cleaning system. This is called as cold system, condenser on-load tube cleaning system. So in this, the sponge balls are there in the cooling water system, which are passing with the cooling water flow through the tube. So if any scale deposition is there in the condenser tube, it is cleaned by means of this sponge balls. So we are utilizing this cold system. Then we are monitoring and maintaining all chemical parameters. Then condenser cleaning by hydrojetting during overall. So for condenser tube cleaning, we are carrying out the hydro ejector jet cleaning of tube during overall. Then HP heater and LP heater performance optimization by adjusting its level, outlet and trip temperature. Because this heater's level optimization plays an important role in heater performance also. If heater level is on lower side, then in that case heat transfer will not be there proper, so will not get the actual outlet temperature. So this has to be maintained. Then parting plate inspection in overall. So during overall, what we are doing, we are checking this parting plate in between, which is there in between the inlet feed water and outlet feed water. So if any damage is there, and this is the main problem of the heater performance, that parting place, because it is in between the high pressure water, so this damage normally takes place. So we are carrying out its rectification during the overall. Then this is the air heater performance. This is for boiler efficiency. Then optimization of auxiliary raw cooling water pump. Then identifying and attending instrument and plant air leakages during unit shutdown, because if any air leakage is there, in that case compressor power consumption will increase. Then regular energy audit and implementing of this recommendation we are carrying out. So our operation and efficiency department is there. He's carrying out monthly online, monthly this offline turbine and boiler performance test by calculating the heat rate and all this. And if any change is observed, then we are carrying it, attending it, try to attending it online or during the overall. And if any, and yearly we are carrying out this energy audit by the external parties such as CII, Godrej and other. So, and we are trying to implement their recommendation. So yearly we are also carrying out this external audit. Then implementation of online energy management system. So we have this ELAN system, energy management system, which directly shows the online power consumption of each and every auxiliary. So daily we are carrying out this energy deviation monitoring. So based on that, we'll come to know which auxiliaries power consumption has increased, and we are attending if it is in on higher side. Then regular monitoring of flue gas outlet temperature, then APH water washing. So these are the some of the best practices which are done for heat rate improvement. Now this is one of the project we have implemented, and that I'll show. Just some photos are there. This is regarding the heat rate improvement by attending parting plate leakage in HP heater 6. As I explained about the heaters, this is HP heater 6. So this is a feed water heater, and it is taking the steam for extraction from HP turbine exhaust, that is CRH. So this is the high pressure heater. In this, this is the feed water line. This is HP heater 5. This is inlet, this is outlet, and this is HP heater 6 inlet, and this is outlet. So this is the HP heater 6. So this is the tube side, and the tube goes like this, and the outlet of the feed water then goes to the boiler. And from this side the extraction steam is there, and to the downside the drain is there. So what happened, this parting plate is there in between inlet and outlet feed water line. So this parting plate normally get damaged, defected due to the high pressure water it is handling. So if any damage is there to the parting plate, in that case, suppose if we compare the parameter for this HP-6, this the at the inlet of the HP-6 the feed water temperature is 205 degrees centigrade, and at the outlet it is around 247 degrees centigrade. So 42 degrees centigrade rise is taking place in HP-6. Now what happened, its temperature due to this parting plate damage, what happened, this 205 degrees centigrade temperature will mix with the 247 degrees centigrade temperature feed water. So its temperature will reduce. So this is a heat loss. So this temperature has reduced by around 10 degree. So what we have done, this high pressure heater, this is the parting plate. You can see this parting plate, normally the welding or any this get damaged, and the heater gets mixed, the feed water from the inlet get mixed with the outlet. So this feed water temperature, we have attended this parting plate defect. So this improved to 245 degrees centigrade from 240 degrees centigrade. So net improvement in temperature by 4.1. It has improved the heat rate by around 3.94, saving of around 87 lakhs. So this is the like this we are taking the so many heat rate improvement projects and trying to implement them. Okay, this is now all about the turbine audit. So after that we'll go for boiler audit. If any doubt or any question on this turbine side, turbine audit or turbine efficiency improvement, we'll take on this, and after that we'll go for the boiler audit presentation later. Amol sir?
Hello.
Hello. Yeah.
Sir, it was a excellent session with giving good insights on this turbine audit. We have one question from.
Yes.
It is, why can't we supply steam coming out from the turbine directly to the boiler?
Oh yes. This is the yes, very good question. Normally some will actually, if we see water and steam, the specific volume of the steam, if you can see, and specific volume of the water, if you can compare. Now this cycle, this is the cycle. Your doubt is very genuine, because what happened, this is a closed cycle. What we are doing, we are condensing the same steam and again feeding that steam, condensing it in the condenser, and then this condensate we are again pumping back to boiler. Now suppose if we want to send this steam again to the boiler, in that case so much high volume, because what happened, the specific volume of the steam is much more as compared to that of feed water. So much high volume steam handling pump is required, and normally steam, I don't think steam can be handled by any pump. So for that purpose, this is the main reason we have to condense it back to the in the condensate or feed water form.
Yes, sir. Sir, there is one more question, sir.
Yeah.
From the student side only. It is, in which season efficiency of the power plant is higher, and why it is so?
Oh yes. Yeah, as we have seen, the efficiency or directly heat rate, in that case, in the presentation also I explained the effect or performance of the condenser plays a vital role in heat rate improvement. Okay. Now this condenser performance, it directly depend on the cooling water performance, cooling water system, and this cooling water temperature, it changes during the ambient as per the ambient condition. Suppose if we consider our power plant, we are located on the coastal area near to the sea. So our sea water temperature means it is not so much changing, but in the with the ambient condition, the water temperature is changing here from, if we see our design inlet water temperature is 32 degrees centigrade. Now we have seen the lowest temperature of around 25 degrees centigrade in the winter night hours and up to 35-36 degrees centigrade during the summer daytime. So what happens if the 25 degrees centigrade cooling water goes inside the condenser? In that case, the condenser vacuum will be more or back pressure will be very less. So if we consider the condenser back pressure very less, in that case, the steam flow required to generate the same output will be less. So the efficiency will be more. So normally we have also seen practically, and this condenser performance is very better during the winter season, night hours. In that case, our efficiency will be more. Hello.
Yes, sir. Yes, thank you, sir.
Yes.
Thank you for your valuable suggestion. Now we'll move ahead to the next session, sir. Over to you, sir.
Okay. Okay. Thank you. Okay. Now we'll go for the boiler audit. Is it visible?
Yes, sir. Yes, sir. It's visible.
Okay. Okay. Thank you once again. Now we'll move ahead for the boiler audit and efficiency improvement. So some initial slides are same what I have explained in the morning. I'll move on these slides. This is a background of the energy audit. Then designated consumers. So as such, there are this and these are the various major areas for energy audit: boiler and turbine. And there are 9 designated consumer. Out of this, power plant is the major DC. This is boiler audit, and these are the same steps which has to be carried out for any an audit. For boiler also, data collection, observation and analysis, then exploration for energy conservation measures, and finally the report preparation. And these are the instruments required for boiler. Now in the morning we have seen the instruments required for turbine audit, but for boiler audit some more instruments are required, because in the boiler side auxiliaries there are so many fans. On the turbine side only CW pump is there, condenser is there, turbine is there, but on the boiler side there is a ID fan, FD fan, primary air fan, air preheater, and all these performance also we have to measure in the boiler side. So we require power analyzer. This power analyzer is used to measure the power consumption, reactive power, power factor, voltage, current, frequency, then temperature indicator, then stroboscope to measure the speed of the driven equipment, then sling hygrometer or digital hygrometer for measuring the density, then anemometer for wind speed. Then online instruments can also be used for measuring, then digital manometer for measuring the pressure, then flue gas analyzer or ORSAT apparatus for flue gas analysis for measuring the oxygen, nitrogen, sulfur, and CO2 in the flue gas, then infrared pyrometers for measuring the temperature, surface temperature, then pressure gauges, then stream trap tester or ultrasonic leak detectors for measuring the leakages, if any. So these are the instruments required for boiler energy audit. Then all these parameters has to be measured and their observation has to be made for conducting the boiler energy audit. First one is the average GCV of the coal, that is gross calorific value. Suppose if we consider the boiler, the input is in terms of the coal what we are firing inside the boiler, and output is output is the steam what we are generating. So for measuring for boiler audit, the main aim is to measure the boiler efficiency, and the average boiler efficiency is in between 80 to 90%. Okay, so for boiler, the output is steam flow and input is the coal flow and GCV. So for that purpose, the coal GCV has to be measured. Then coal composition, ultimate and proximate analysis of the coal for calculating various losses which are taking place in the boiler. Then coal consumption details. The coal consumption is the critical measurement for boiler efficiency, because it has to be very accurately calibrated for coal consumption. Normally, the coal consumption is measured from the gravimetric feeders, where load cells are there, which measures the coal flow, which is fired inside the boiler. Then performance parameter of coal mill. Then heat rate also is to be measured for unit efficiency. Then steam parameters, their flow, pressure and temperature. Then air parameters also, flow, pressure, temperature. Then flue gas, flow, pressure, temperature. Then flue gas analysis, coal consumption, ambient temperature, boiler loading. Then motor electrical parameters. Then surface temperature of insulation is also required to be measured of boiler surfaces for calculating the radiation loss. Then unburnt composition of the in the fly ash and bottom ash for calculating the unburnt carbon loss. So these are the measurements are required and for the boiler audit. This is general about the power plant we have seen in the morning, conventional, non-conventional. This is the modified Rankine cycle. This is the boiler cycle we have seen. So for boiler, the coal mill performance need to be measured, coal parameters, and exhaust of the boiler. The flue gas goes to the air heater, then air heater parameters also required. Then finally ESP, ID fan, GD, and to the chimney. So this is the air and flue gas cycle. These are the losses. Now, if you can see the boiler efficiency, if you consider this boiler, so the coal which is fired inside the boiler, if you consider this example, suppose 120.7 tons per of coal is fired of GCV 4000 kilocal per kg. So 120.7 into 4000. So the heat input is 482.8 million kilocal per hour. Okay, and output of the boiler is steam flow. So steam flow, and we can calculate if it is 420 million kilocal per hour. In that case, the output of the boiler is 420 and input is 482. So boiler efficiency will be 420 upon 482. It comes around 87%. So this is the boiler efficiency. So for calculation of the boiler efficiency, we need to calculate the output and then it divided by the input. These are the performance terms we have already seen. Now boiler efficiency. Now for as per the ASME PTC code, then we have to calculate the boiler efficiency. So the boiler efficiency calculation is by two methods. One is the direct method and the other one is the indirect method. So in direct method, the energy gain of the working fluid is compared with the energy content of the boiler fuel. Means we have to calculate by direct method output upon input. And in indirect method, the efficiency is the difference between the losses and the energy input. It is most widely used. There are different advantage and disadvantage of both these methods. So in indirect method, we are calculating the losses and subtracting it from 100. If we consider the 100% input, and if we can come to know or calculate all the losses, then we have to subtract the losses and we'll get the boiler efficiency. So this boiler efficiency, two methods. So by direct method, it is heat output upon heat input, and heat output is heat in steam. So the steam generated by the boiler. So how much is the heat content and how we can calculate the heat content of the steam? It is based on the enthalpy of the steam, that is pressure and temperature of the steam at the outlet of the boiler. And heat input is in kilocals by means of fuel. So coal flow into GCV of the coal, that we can calculate the heat input and we can divide it for the heat steam output. And in indirect method, this boiler efficiency is calculated upon by 1 minus summation of all losses. So these are the two methods, and the most majorly used is the indirect method. So we'll see next what are the advantage and disadvantage. The direct method, and this is input output method, is also common name. It is calculated as the percentage of heat utilized by feed water in converting it to steam to the heat released by complete combustion of the fuel used in the same time. So boiler efficiency by direct method, it can be calculated the same MS flow into MS enthalpy minus feed water enthalpy plus CRH flow into HRH enthalpy minus CRH enthalpy. This is the output of the boiler. We have seen the same term used for the heat rate because this output of the boiler, it is input for the turbine. So for gross turbine heat rate also we have used this term. So this is heat input to the turbine and this is output of the boiler, and input to the boiler is fuel firing rate into GCV plus some heat credit if it is any. So we can calculate this boiler efficiency by this direct method by using by this formula. Now by indirect method, suppose if we consider the fuel input as 100%, this is the boiler and we are giving some excess air for a complete combustion, and this is the steam output, this is output, and the difference between this output is the losses. So if we can come to know all these losses, then we can calculate the efficiency by 100 minus all these losses 1 to 8. So what are these losses? Then we'll see. These are the losses. One is the dry flue gas loss, which is taking place by the exhaust of the flue gas. Then hydrogen loss due to moisture in air and moisture in fuel. Then CO loss, then fly ash loss, bottom ash loss, and surface loss. This is the radiation loss. So if you calculate all these losses and subtract from 100, then we can get the efficiency by indirect method. Now this is the comparison of direct and indirect method. The direct method calculation is based on coal flow and steam flow. This calculation for indirect method, it is based on boiler loss. And total output is calculated. 1% error in measurement result in 8% in boiler efficiency. The major difference is that there are so much chances of error in this direct method because only 2-3 parameters are there: coal flow and steam flow and GCV. So if any 1% is error in the coal flow or any steam flow parameter, then the efficiency deviation will be by 8%. But here we are calculating only the loss. So 100 minus loss. So any change in loss by 1%, it does affect the efficiency by only 2%. So here in direct method, there are much more chances of error. So this is less accurate, but indirect method is more accurate. And this direct method do not give any significance where improvement to be done, because if we calculate the boiler efficiency by direct method, we will not come to know where to act upon, because we are not knowing. Suppose earlier the efficiency was 90%, now it is 85%. Then why it is so? We will not come to know by the direct method. But in indirect method, as we are calculating all these 8 losses, so any loss, if it is going to change, then it affects the efficiency. So we can directly come to know which loss has changed, and accordingly we can act upon. So, but the direct method is easy to calculate. It is complicated, but it is accurate. Normally, the boiler efficiency is in the range between 75 to 90%, depending on the performance and maintenance of the boiler. So these are some general values of all these losses. Suppose dry flue gas loss. The dry flue gas loss, it is due to the high temperature of the exhaust flue gas, because all this flue gas, it is directly sent to atmosphere through two chimney. Suppose the air from the inlet we are taking at 30-35 degrees centigrade, and if the flue gas, it is sent to atmosphere at 100 degrees centigrade, means so much heat is lost. So this comes under the dry flue gas loss. So we have to reduce the exhaust flue gas temperature as much below as possible, but there is some limitation for this, and that limitation is due to acidic dew point. So we can't go below 120 degrees centigrade the flue gas temperature, because the sulfuric acid formation will be there below 120 degrees centigrade, and it will damage the ducting and all other parts. So minimum flue gas temperature we can achieve is 120 degrees centigrade. Then unburnt and combustible radiation and unaccounted losses, these are average around 2%. Then losses due to moisture formed by hydrogen combustion, due to this is around 3.7%. Then losses due to moisture in fuel, it is 0.2%, and losses due to moisture in air is 0.1%. So around average 11% losses are there. So the boiler efficiency is 89%. So now these losses and their affecting parameters: sensible loss, that is dry flue gas loss. Then wet flue gas loss, it is affected by moisture in fuel. If the moisture is more, then wet flue gas loss is more. In that case, more combustion is required. Then moisture in air and moisture due to hydrogen in fuel. So these all three form the wet flue gas loss. Then loss due to incomplete combustion. If the combustion is not complete, in that case CO formation will be there, then heat loss will be there. So that is, this loss is due to CO formation. So complete combustion we can ensure by complete formation of the CO2. If no CO formation, that is carbon monoxide formation is there, then in that case complete combustion will be there. Then loss due to carbon in bottom ash and carbon in fly ash. Because what happens when after combustion the ash is generated, if some unburned carbon is there, then it carries away with the ash. So this is loss due to carbon in bottom ash and fly ash. Then radiation and convection losses. So these are all losses, and on which parameter it depends. Now we can calculate this boiler efficiency by calculating all these L1 to L8 losses. So 100 minus L1 to L8, we can get the boiler efficiency by indirect method. Now, what is the data required for indirect method? Now, all these losses, these 8 losses, we need to calculate. So, to calculate each and every loss, we need this data. So, first one is we need ultimate analysis of fuel, that is coal. So, the ultimate analysis contains hydrogen, oxygen, sulfur, carbon, moisture content, and ash content. Then percentage of oxygen or CO2 in the flue gas. So after combustion, how much oxygen is generated and CO2 is generated, that we need to know. So we need to have the analysis of the flue gas. Then flue gas temperature at APH outlet to calculate the dry flue gas loss. Then ambient temperature, that is secondary air inlet temperature. Then GCV of the coal, that is gross calorific value. So our plant is designed for 3,700 kilocal per kg GCV, but there are different types of coal having different GCV. So here at Dhanu we are using blending of coal, that is we are mixing the Indian coal with the imported coal, and there are different advantage and disadvantage of both these coals. Imported coal has high GCV and also less ash content, so its efficiency, if we fire this imported coal, then efficiency, boiler efficiency is more, but it depends on the design of the boiler. Then percentage of combustible in ash, then percentage of CO in flue gas, and GCV of ash also is required in kilocal per kg for indirect method. So if all these parameters we can get, then we can calculate each and every individual loss. This is the boiler efficiency monitoring sheet. So what parameters we have discussed, this we have to monitor, we have to get all these parameters. So if calibrated instruments are already there in the system, we can get these parameters on from that only, or offline instruments has to be used. Suppose the external auditor is there, then they will bring their own instrument and calculate all these parameters, and from this directly we can get all these losses. So we have our sheet and our software package inbuilt in the system. So because all these parameters are there in the system which are under continuous monitoring, so from that continuously we are getting the boiler efficiency directly. This is the coal analysis, proximate and ultimate analysis. It is required by the chemist for calculation of all these losses. This is the final output of our one of the unit, which shows all the parameters and all the losses. We can see the pitch outlet temperature, inlet temperature, then coal data, then distribution of ash and all these parameters. From that, the boiler efficiency is calculated. So all these losses are calculated, and 100 minus all these losses, we can get the boiler efficiency. Now the boiler efficiency, it depends on the measure, because in the boiler what is taking place? Combustion is taking place. If the combustion is proper, in that case the boiler efficiency will be maximum. So we have to control the combustion. We have to maintain all these parameters on which the boiler efficiency depends. Now, how to control the combustion? It is totally depend on the operator, how to ensure the proper combustion. As we have studied, the combustion refers to rapid oxidation of fuel accompanied by the production of heat. So during combustion, what happens? The heat is generated. So proper combustion, the 3 T's of combustions are required. The 3 T's are time, temperature, and turbulence. So temperature high enough to ignite and maintain the ignition of coal. Then turbulence or intimate mixing of fuel and oxygen. So for temperature, we are using the air preheater. So in air preheater, the air temperature, that is primary air and secondary air, which is coming to the boiler, its temperature is increased. So at the inlet of the boiler, the primary air and secondary air temperature is of the range around 300 degrees centigrade. Turbulence, this turbulence is ensured by the burner design, so that the coal which is entering the boiler, it is turbulated. Then time sufficient for complete combustion. So the draft is maintained in the boiler to ensure the sufficient time for complete combustion. So these 3 T's are necessary for complete combustion. Now this is the oxygen required for combustion. If we consider hydrogen for its oxidation, around 28,920 kilocal kg of heat is liberated. So 1 kg of hydrogen requires around 8 kg of oxygen. Carbon C plus O2, around 8084 kilocal per kg of heat is liberated, and 1 kg of carbon required 2.67 kg of oxygen. Sulfur, for sulfur dioxide function, 2224 energy is liberated, and 1 kg of sulfur requires 1 kg of oxygen. So for 1 kg of oxygen, air required is 4.34. So total, so much times air is required, and this air is supplied by means of the FD fan, that is secondary air fan, for complete combustion. That is known as the excess air. Now this is the oxygen required for combustion if we compare perfect combustion, good combustion, and incomplete combustion. The perfect combustion, if you can see at the outlet, it is CO2, H2O, N2, and so it is the actual how much amount of air is required, only that much amount of air if it is fed to the boiler, then it's a perfect combustion. But as the system have some leakages and all this, so perfect combustion is not possible. Means zero excess air if we can give, then it's a perfect combustion. But for good combustion, we need to give some excess air. So every boiler is designed for 20% normally excess air. So for that purpose, how we can ensure the good combustion? So by monitoring the oxygen in the flue gas. So we normally at the air preheater inlet, we are maintaining 2% oxygen in the flue gas. So we can ensure the good combustion is taking place in the boiler. And this is the incomplete combustion. If the design air which is required for the complete combustion, it is not supplied, if less air is supplied, in that case incomplete combustion will be there and CO formation will be there, and this CO is carried in the flue gas to the atmosphere through chimney. So much heat is lost by incomplete combustion. So how we can ensure good combustion? By providing the excess air for the combustion. So if you consider, if CO formation is there, in that case 2430 kilocal per kg of heat is lost. So around 70% of the heat is lost due to incomplete combustion. Now these are the factors which are affecting the boiler performance. So boiler performance, it depends on the boiler condition, means what are the instruments, equipments which are there in the boiler. So their condition if their condition is good, in that case the boiler performance is better. The boiler condition, burner condition, so these burners are used for firing the coal, oil. So if the burner condition is good, in that case the performance of the boiler is better. Then air preheater seals and basket. In air preheater, as we have seen, the heat from the flue gas is given to the surrounding air. If the seals are get damaged, in that case the bypassing of the air takes place, so that heat is lost. So we have to maintain the seal and basket condition. And also in the air preheater, steel baskets are there, so which absorb the heat from the flue gas and give this heat to the surrounding air. So if the basket condition is also not good, in that case the boiler performance will not be there. Then air ingress in the boiler system, if it is there, because what happen, the boiler furnace, we are maintaining slightly negative pressure, that is furnace pressure on slightly negative side. Can anyone give the reason why the furnace or boiler pressure is maintained slightly negative? Hello? 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 Am I
Sir,
audible?
we know the negative pressure in the condenser, but why it is required, we don't know.
Okay. Yeah. The main reason to be maintained, the furnace pressure to be maintained in negative side, it is because what happened in the boiler, what is there? The flame is there, combustion is taking place. Suppose the boiler pressure is positive, in that case what will happen? The flame will try to come outside the boiler. So normally the furnace is slightly maintained negative, that is -10 to -15 mm of water column. But if it is on more negative side, in that case air ingress will be more, so boiler efficiency will be less, boiler performance will get deteriorated. So slightly negative only, so as to avoid the flame going outside the boiler, because in the boiler for checking the flame condition there are so many peepholes where the operator can watch the flame condition. So if any peephole is in open condition, slight openings are there, normally kept purposefully in the boiler so as to watch the flame condition. So if the furnace pressure is on positive side, the flame will come on the outside and it will affect the safety of the boiler area. For that purpose, the boiler pressure is maintained slightly negative. Okay. Then insulation of the boiler also plays a vital role. If the insulation condition is not good, in that case the boiler radiation losses will be more and boiler performance will get deteriorated. And also some operating parameters such as excess air optimization, soot formation. Soot formation is on the boiler inside there are water wall and superheaters coils are there. So if any soot formation is there on the coils or water wall, in that case heat transfer will not take place. What happen in boiler, the heat transfer is taking place, means the combustion heat is given to the surrounding water wall and superheat. So if soot formation is there, in that case the heat transfer will not be there, so maximum heat is lost to the surrounding. So for that purpose we have to clean the soot. Then burnal tilt, this burnal tilt are used for maintaining the reheat temperature. So this burner can be moved from +30° to -30°. Then wind box pressure has to be monitored. So all these are the operation parameters which affect the boiler performance. Then chemical properties, chemical parameters, we have to maintain the water chemistry and coal properties. So these are all the factors or parameters which are affecting the boiler performance. Now, similarly, we have seen for heat rate. These are some of the thumb rules for boiler efficiency, boiler performance. Any 5% reduction in excess air increases boiler efficiency by 1%. Means if excess air, if it is on higher side, in that case, it is affecting the boiler efficiency. If we can reduce the excess air, in that case, the boiler efficiency can improve by 1%. Then 22 degrees centigrade reduction in flue gas temperature increases the boiler efficiency by 1%. So if the exhaust flue gas temperature is more, in that case boiler efficiency will be less. So we have to optimize the boiler exhaust flue gas temperature up to minimum value of 120 degrees centigrade. Also 6 degrees centigrade rise in feed water temperature brought about by economizer condensate recovery correspond to a 1% saving in boiler fuel consumption. Then 20 degrees centigrade increase in combustion air temperature preheated by waste heat recovery result in 1% fuel saving. Also, if the air which is going to the boiler, primary air and secondary air, if its temperature is increased by 20 degrees centigrade, then it will result in saving in 1% of fuel saving. Because if high temperature air or water is going to boiler, so in that case lesser coal is required to burn to maintain the or to generate the steam. And also a 3 mm diameter hole in a pipe carrying 7 kg of steam would waste around 32,650 liters of fuel oil every year. So this is the impact of any steam leakage is shown here. So we should not neglect any steam leakages. So if any steam leakage is there, should try to attend it as early as possible, because the steam leakage is directly wasting the steam to the atmosphere and unnecessary reducing the boiler efficiency or losses. This is the graph showing the impact of excess air. Now we can see this is the excess air. Excess air means the air which is fed by FD fan, that is secondary air fan, to the boiler. Normally the PA fan, that is primary air, is carrying the fuel to the boiler. But this FD fan is supplying the excess air for complete combustion of the fuel in the boiler. If excess air, we can see on the left side, if it is on lesser side, in that case, we can see as per the graph, the CO formation is maximum. But as soon as we can increase the excess air, the CO will reduce. So at 0% excess air, this is the perfect combustion. But the efficiency, we can see this is the top graph. It is least on the excess air on very low side, but it is maximum on excess air designed at around 15 to 20%. So 15% reduction in excess air increases boiler efficiency by 1%. So this is the maximum efficiency point. So if it is the excess air is in between 15 to 20%, then the boiler efficiency is maximum, and CO, that is unburned carbon, is also minimum, and we can ensure the excess air is there by observing the O2% in the flue gas. But we can see after this point, if the excess air is increased, we can see that the efficiency is also falling. Because what happens if the excess air is increased after 15-20%? In that case, the oxygen is increasing, because the air which is required for the combustion is much more than the excess air. So this oxygen will increase, but efficiency will fall, because this excess air is supplied to the boiler. It will reduce the temperature of the boiler and it will affect the combustion. So the efficiency reduce. So the optimum efficiency point is at 15 to 20% excess air. And below this optimum excess air point, the CO formation will be there. So we have to avoid this unburned carbon loss, ensure that excess air is supplied as per the design value. Now what I have told about the soot formation, because inside the boiler, these are some of the coils of boiler. This is one of the Platon superheater coil. You can see on the left side figure, this is the soot deposition, because what happens when combustion takes place, the flue gas is generated and clinkering formation takes place, and it sticks onto the coils of the boiler tubes. So what happens when this soot deposition takes place? Because in this tube, the steam or water will be there, and outside this, the firing is there, combustion is taking place. So what happens if the deposition is there? In that case, the heat transfer is affected. So 100% heat transfer will not be there. So our boiler efficiency will reduce. So to remove this soot deposition, the soot blower system is there. So soot blower system is same. It is removing this soot. So this is the external device which goes inside the boiler, and at the tip of this the nozzles are there. So it send the steam inside near to this coil, and it will remove all this soot, and this steam is carried away in the boiler. So after soot blowing, these coils become like this. So if this deposition reduces, in that case the heat transfer will improve. So this is the thumb rule. A 3 mm thick soot deposit on a heat transfer surface can cause a 2.5% increase in fuel consumption. Because what happens if this soot is there, in that case heat transfer will not be there. So our efficiency, boiler efficiency will reduce, and it will increase the fuel consumption. Now for the soot blowers, soot deposit result from combustion of coal or oil in the furnace. Also, we are using oil firing during startup of the furnace because directly coal cannot be fired. So in the boiler, the oil is first fired, and after getting the sufficient ignition energy, then only the coal is fired. And so it is necessary to remove the deposit which is settled on the tube. This soot deposition, it reduces the heat transfer rate of the tube. For this, soot blowers are utilized to clean the deposit and to improve the heat transfer. For this, there are two types of soot blowers are there. Water wall soot blowers. So these are short in length. They are near to the water wall surfaces. So it is of the length of around 0.5 meter only. And it removes the soot from the water wall tubes. And these are the LRSB, that is long retractable soot blowers. Their length is around 4 to 5 meter. So this remove the soot of the superheater coils. So these superheater coils are there in the horizontal pass, that is LTSH, platen superheater, reheater, and final superheater. So all these superheater coils soot is removed by means of this long retractable soot blower. The medium used for soot removal is normally steam, but in some plant air, this is known as ultrasonic soot blower, or sound is also used to remove these soots. Now other equipment or this for boiler performance is wind box assembly and burner. You have seen these burners. Through this burner, the coal firing is taking place. So proper condition of the burner should be there for the boiler performance. Burner tilts of all kernels should be equal and auto control to maintain the reheater temperature. Secondary air control dampers should be operative. So all these dampers which are there in the secondary air line for ensuring the excess air for the combustion, they should be operative. Then wind box differential pressure to be maintained in a range of 80 to 120. Normally this wind box, it is in between the furnace and the secondary air. So its pressure, it should be between 80 to 120 mm of water column. If the wind box and furnace differential pressure is more, in that case the flame size will be less, and if it is less, the flame will touch the water wall tubes, so it may affect the tube leakage of the boiler. These are the boiler burner conditions. So this is a good burner to ensure the turbulence of the fuel. Through this PC pipe, the fuel is fired inside the boiler, and this is the damaged burner. So we have to maintain the burner condition. The poor burner condition leads to high unburnt carbon, poor combustion, clinkering, external coal leakages, and poor flame stability. So we have to maintain the burner condition. Normally these burners are replaced during overall after every 2 years. Now this boiler efficiency loss, it depends what all the losses we have seen, all 7-8 losses. There are some controllable losses and some are the functions of the coal quality, because the what coal quality we are receiving, that is not under our control, but other operating parameters which are our under control, that we can control. So we can control the boiler efficiency loss through operation of this boiler parameters. That is controllable loss are due to parameters, that is dry flue gas loss. So we have to reduce the dry flue gas loss by reducing the flue gas exhaust temperature. Then unburnt carbon loss we can reduce by proper combustion of the fuel, providing sufficient excess air. and proper milling condition also reduce the unburnt carbon loss. Then CO loss can be reduced by optimizing the excess air. Then radiation and convection losses can be reduced by ensuring the insulation at all areas. So if any insulation gets damaged, in that case we have to do the corrective action. And these are the some parameters which are function of the coal quality and affecting the boiler loss, that is loss due to moisture in coal. So what coal we are getting, that we don't have under our control. Then loss due to hydrogen in coal, and loss in ash, that is sensible heat. Now how we can optimize the boiler efficiency? So first one is the dry flue gas loss. How we can reduce the dry flue gas loss? We have seen we have to optimize the excess air. If the excess air is more, then dry flue gas loss is more. Then minimize cold air damper of the coal mill. Then operation of air filter and furnace soot blowers. So if soot deposition is more, then what happen? The exhaust flue gas temperature, because the flue gas will not give the heat to the water wall or superheater. So the heat is carried away by the flue gas. So dry flue gas will increase if the soot deposition is there. Then air filter basket replacement and seal replacement and setting has to be done adequately during the overall to reduce this dry flue gas losses. Then arresting of air ingresses and burner tilt auto operation. So these are the things which can be done to optimize to reduce the dry flue gas loss. Then unburnt carbon and CO loss. Unburnt carbon is due to the improper combustion, that is if CO formation is there, and also if the pulverized coal which is going to the boiler, if its size is on higher side, in that case it will not play a role in combustion. So its combustion will not take place, and higher weight or higher density particle will fall down in the bottom ash hopper, and this unburnt will go in the bottom ash. So for this, the milling system should be adequate. So its performance should be okay, so that the unburnt will not be there. So to reduce this unburnt carbon loss and CO loss, we have to optimize the excess air. So if excess air is less, then CO loss will be there, unburnt carbon loss will be there. Then coal fineness of the coal mill has to be carried out. Normally, for boiler is, suppose any pulverized coal boiler is there, the pulverization, that is pulverized coal size is normally 70% of 200 mesh. This is the screen size. So if the screen size is means the size of the coal particle is more, in that case the unburnt carbon loss will be more. So this is the impact of unburnt carbon in bottom ash and fly ash. Any 1% or increase in this unburnt carbon in bottom ash and fly ash by 1% will affect the boiler efficiency by 0.1 and 0.5%. And if excess air is more than by 15%, then boiler efficiency deviation is by 1%. Then air inter gas outlet temperature, which is the main reason for the dry flue gas loss. So the main reason for this APH outlet gas temperature is ineffective APS soot blowing. So air filter, similarly we have seen water wall soot blower and long retractable soot blower. Similarly, soot blowing mechanism is there for the air filter. So if APS soot blowing is not carried out, then APH outlet flue gas temperature will increase. And also deposit on boiler heat transfer surface will increase the APH outlet temperature. And if low final feed water inlet temperature, then firing will increase to, and it will increase the APH outlet temperature. Then using upper rows of burners on low loads, normally different elevation burners are there. So if upper elevation burner is there, in that case APH outlet temperature will increase. And if also excess air increases, then APH outlet temperature will increase. The final gas temperature around 20 degrees centigrade, if it is changed, then it will affect the boiler efficiency by 1%. Then combustible in materials in ash, that is unburnt or CO. The permitted value of carbon in ash are 0.8% in fly ash and 4.8% in bottom ash. Values greater than the above are indicative of poor grinding, incorrect combustion air supplies, and incorrect pulverizer fineness classifier setting. So these are all due to the coal mill performance. If proper grinding is not taking place in the coal mill, in that case, the unburnt carbon in bottom ash and fly ash will increase and it will affect the boiler efficiency. So any 1.5% carbon in ash is equivalent to 0.5% boiler loss. That is, boiler efficiency is affected. Then boiler excess air, boiler combustion efficiency depend on supplying correct quantity of excess air. Supplying too much excess air will increase the dry flue gas loss. This is because the quantity of gas will increase and so will absorb more heat content, as excess air will absorb heat more readily than the heat exchange surface, thus increasing the air outlet temperature. So 1% change in excess air reduces boiler efficiency by 0.05%. And how we can optimize the boiler efficiency? Then for radiation and convection and other losses, one of the loss, that is radiation loss, is quantum is less, but we can also reduce the radiation loss by carrying out boiler insulation survey, because the boiler on the water wall external side, the insulation material and sheet is provided. So if any insulation material is damaged, in that case radiation loss will be there, so it will affect the boiler efficiency. Then we are to arrange the steam leakage, then arrange the passing of high energy drain walls, then minimize the air ingress and arrange the air leakages. So by this way, we can reduce the radiation and convection loss and other parameters to improve the boiler efficiency. So these are the various factors affecting the losses. We have seen dry flue gas loss. It is due to flue gas temperature, excess air, fuel analysis. Then loss due to moisture formed from hydrogen and fuel. It is due to hydrogen containing fuel, flue gas temperature and fuel analysis. Then loss due to moisture, fuel moisture. It is due to moisture in fuel and flue gas temperature. Then loss due to moisture in air is due to humidity of combustion air. If the humidity of inlet air is more, then loss due to air in moisture is more. Excess air level, if it is more, then this loss is also more, and it is also due to flue gas temperature. Then radiation and convection loss, this is due to insulation of boiler. Then unburnt carbon in bottom ash and fly ash is due to fuel analysis, and unburnt carbon due to milling system. And sensible heat loss in ash, it is due to ash temperature and fuel analysis. This is the summary of all the parameters, and it's due to the its deviation, how much the boiler efficiency is deviated. Now, these are some of the methods to control the carbon loss. Good burner maintenance, ensuring consistent mill fineness, so mill performance, proper secondary air adjustment, reducing primary air to minimize most possible, because the main function of the primary air is to carry the coal. So we have to optimize the primary air and provide sufficient secondary air and ensure excess air for complete combustion. Then cut out oil support at higher load where coal flame is stable, as oil preferentially deplete O2 in the area and reduce O2 for coal particles to burn. So normally this oil firing is done to ensure to provide the ignition to the coal. So after 40-50%, we can cut out the oil support and ensure only coal is in service. So we have to cut out the oil flame. Then check coal property and tune combustion. Daily, this ultimate and proximate analysis has to be done, and accordingly, combustion tuning should be done. Keep boiler heat transfer surface clean so that losses can be reduced, thus reducing the coal input. This can be done by proper soot blowing. So these are the factors affecting the boiler performance: periodical cleaning of boilers, soot blowing, proper water treatment program and blow down control, then draft control, excess air control. Percentage loading of the boiler also affect the boiler performance. So if the loading is less, then the boiler performance is also affected. Boiler efficiency will be less. Steam generation, pressure and temperature, boiler insulation, and quality of fuel. These are the factors affecting the boiler performance. Some checklist for proper good performance of the boiler. So we have to look for any leakages, gauge glass, and check for water column. So if any leakages is there, then try to arrest it during running. Open inspection door and check for slag accumulation. there are peepholes or inspection doors are there in the boiler. Normally during round we have to check this, and if any accumulation or slack formation is there, that we have to check inside the boiler. Check for unusual noise and listen for tube leak. So during normal round, the operator has to ensure any sound. If any tube leakage sound is there, then we have to carry out the shutdown of the boiler and attend the tube leakage. Because if the tube leakage is not attended on time, in that case, it may create the secondary damages and multiple failure also may occur. Then overheating and adequate lubrication of on motors. Check that no soot blowers are stuck and no leaking inside the boiler. Burnal tilt and secondary damper control, uniformity in all corners. So all corner, this burnal tilt and damper should be at same level. At firing floor, check for any fuel leak, because near the boiler area, since it's a hot, if any oil leakage is there, then unnecessary fire will be there. Check all vertical coke pipe for any choking and overheating. Then these are the some practices for combustion optimization. Indian high ash coal result in high primary air requirement, that is primary combustion dilution. Indian coal, so primary air requirement is much more. Secondary air distribution at required elevation is very important. So depending on the oxygen measurement in the flue gas, we have to distribute the secondary air at all elevation. Then avoid, reduce all unwanted secondary air at any location and divert them to other needy elevation. This is normally because the coal firing which is taking place at that elevation only we have to provide the secondary air for combustion. Suppose the unnecessary secondary air is given to the elevation where the coal firing is not taking place, we have to cut that secondary air. Then keep mill airflow just above settling velocity, proper velocity has to be done. Then keep total airflow in the range of around 20% excess air. Keep furnace to inbox DP in the range 100 to 150 mm. Then operate water wall soot blower as per the practice or as per the furnace flue gas temperature observation. So by checking the flue gas temperature, we can see which area soot blower has to be operated. Then top mill combination wall blower 3 and 4 twice per week. If the top mill operation is there, in that case wall blower requirement is more, so we have to change the frequency accordingly. And before a plant shutdown, operate all water wall soot blowers so that the furnace is ensured completely cleaned. Then these are the some excess air damper control, that is secondary air control. These are the AA damper, then fuel air damper. So all the elevation where the firing is taking place, its fuel air damper should be kept around 40 to 50% open. Then check and ensure the same position of SADC, that is secondary air damper control, to ensure the complete excess air, sufficient oxygen at all level. Then opening of OFA and top AAD on non-working elevation, it depends on the urban fly ash and superheater radiator temperature and splay. And also overfire dampers are used for controlling the NOx measurement. So if NOx on higher side, then OFA dampers are open. So at higher temperature, the NOx formation is more. So by opening the OFA damper, we can reduce the NOx. This is the just last point. One case study I will show about the boiler efficiency improvement for the soot blower operation. So what we have done at our side. Normally the soot blower are earlier are conventional. So as per the OEM recommendation, we are operating the soot blowers. So for LRSB, once in a week we are operating all soot blower. Water wall soot blower daily we are operating, and air filter soot blower we are operating once in a shift. So if the soot blower are more as compared to the required, in that case unnecessary the lower efficiency erosion of tube may take place, DM water consumption will be more. But what we have done, we have identified and we have analyzed all the boiler area, flue gas pressure and temperature, and now based on that flue gas temperature pattern, we have prepared our scheduler, and based on that temperature we are operating our soot blowers. So this is as per the requirement only now we are operating. So Earlier the soot blower was operated based on the time base, frequency base. Now we have optimized this to as per the requirement. This is the one of the animation for the LRSB. This we can see, this is the LRSB long retractable soot blower operation. This is boiler outside, and this is the superheater coils inside the boiler. So if any soot deposition is there, this LRSB will go inside and this steam valve will open and will send the steam to this tubes, and it will remove the all soot deposition. So we have prepared our this scheduler for long retractable soot blower based on the flue gas temperature in various zone. So, and we have identified if that particular zone, so flue gas temperature is on higher side, then we are operating that long retractable soot blower only. So this is our scheduler, and by entering only the flue gas parameter, we will come to know which soot blower has to be operated. So we have developed this soot blower scheduler in house. So earlier it was conventional approach. Now it is an intelligent approach. So earlier it was only time-based soot blowing mechanism we are operating. Now it is as per the need base. So the area where the soot deposition is more, that scheduler is taking the analyzing where the soot blowing mechanism is required, and based on that only it is giving the suggestion for operating the soot blower in that area. This is the same boiler parameters and its impact on boiler efficiency and heat rate. So we can see the change in boiler efficiency by around if we 1.4%, it will change the heat rate by around 36.8 kilocal per kilowatt hour. So this is the impact of boiler efficiency on the heat rate. Okay, thank you. This is all about the boiler audit and boiler performance improvement. Now regarding this, if any questions or any doubts are there, we can discuss now.
Yes, sir. So thank you for your excellent insights on this boiler audit and performance of boiler systems. Sir, there is a question from Dr. Siddhappa Bushnur.
Okay.
How do you come to know that there is a air leakage in condenser when the plant is running?
Yeah, actually this is one of the practical problem or practical situation in the condenser. As I said, the vacuum is maintained or back pressure is maintained in the condenser due to condensation of the steam inside the condenser. But there are some non-condensable gases or thing which are there in the condenser which will remain. So all these gases has to be removed. For that purpose, vacuum pump system or ejector system is there. So this remove the non-condensable gases inside the condenser. Now on the discharge of this vacuum pump, there is a rotameter. It is one of the flow meter for measuring the air flow. So this rotameter flow measurement, we are doing it in shift monitoring, and daily in within the shift we are monitoring this rotameter reading. So normally it is for each vacuum pump there are two vacuum pump. So in our case I can explain around 40 to 50 meter cube LPM that rotameter reading is there. So daily we are doing the monitoring of that. If that flow increases, then we'll come to know that there air ingress is there inside the condenser. Now second another thing we can come to know by monitoring of the back pressure or condenser vacuum, because we have daily reading of that. So if that back pressure of the vacuum air ingress is there inside the condenser, now next step is to identify from where this air ingress is there. So for that purpose we can carry out the routine round of the condenser area and all the piping which are connected to the condenser. So if by sound or visual inspection if we can identify, then it's well and good and we can attend if it is possible. Otherwise we have to carry out this helium leak test. Means this is the external testing facilities there. There are so many vendors for carrying out this helium leak test in the condenser. So they are sending this helium gas near the condenser area, negative points, and they are checking the helium detection at the discharge of the vacuum pump. So all negative points, all means vacuum points which are near the condenser, they are sending the helium. So at which point they are getting the maximum reading for the helium at the vacuum pump discharge, they can come to know, identify that particular disk system, that air ingress is there from this point.
Yeah, thank you, sir. There is one more question, sir, from Dr. Siddhappa Busnur again. How variable frequency drive helps in heat rate improvement in boiler?
Yeah, actually, the variable frequency drive, it doesn't directly help in the boiler, because variable frequency drives are used for reducing the power consumption of the auxiliaries. So what happens if we install the variable frequency drive VFD? This power consumption of that auxiliary will reduce. So our auxiliary power consumption will reduce and our net output will increase. So overall net heat rate there will be impact on the net unit heat rate by the variable frequency drive. So at our unit also we have installed VFD on so many auxiliaries such as the CEP, condensate extraction pump. This is the high capacity pump. So we have installed the VFD for that particular drive. So our power consumption has reduced. So particularly for CEP, this is a big drive. Earlier its power consumption was in the range of 600 kilowatt. Now it is in the range of 400 kilowatt. So by each CEP, for each CEP, the power consumption has reduced by 200 kilowatt.
Yes, thank you, sir. Sir, there is one last question from Professor Vivek Agarwal. He's asking, why do we run condenser at vacuum pressure?
Yeah, yes.
Sir, should I repeat the question?
Yeah, please.
Sir, the question was, why do we run condenser at vacuum pressure?
Okay. Yeah, condenser, normally the vacuum is maintained inside the condenser by means of the condensation of the steam. Because what happened, the steam which is coming from the LP turbine, its condensation is taking place in the condenser. So what happened, the specific volume of the steam is reducing, and the exhaust steam from the LP turbine, it is getting condensed and the condensate is formed. Now this condensate is then pumped by means of condensate extraction pump. So during this condensation, the vacuum is generated, vacuum is maintained in the condenser, and this vacuum is required for reducing the back pressure of the turbine, LP turbine. So if the back pressure is on lower side, in that case, the exhaust steam from the LP turbine will come to the condenser, and this vacuum pump is only utilized for removing the non-condensable gases which are there in the condenser to remove.
Yes, thank you. Thanks a lot, sir, for clarifying all the additional questions asked by the audience. Now I will request Professor Pierre Poddar to give the vote of thanks. Over to you, sir, Poddar, sir.
Okay, thank you.
Am I audible?
Yeah, yes,
yes,
yes.
sir.
Yeah. Thank you, Panaskar, sir. It is my privilege to propose a vote of thanks on this occasion. I, Professor Parmeshwar Kaur, on behalf of MCT's Rajiv Gandhi Institute of Technology, Department of Mechanical Engineering, and on behalf of Organizing Committee of AICT AQIS, sponsored online one-week short-term training program on recent trends in energy management and audit, and on my own behalf, extend a very hearty vote of thanks to Mr. Pawan K. Sharma for accepting our invitation as resource person and sparing his valuable time with us. He has given good insights on the topic of turbine audit and boiler audit. Under this, he has discussed need of energy conservation, losses in power plant, efficiency and heat rate, factors affecting heat rate, best practices to improve boiler, turbine and condenser performance, and many more. So thank you so much, sir, for giving the information. It's a very good information for all of us. So thank you so much, sir. With this, I declare that the today's session is over. Tomorrow, 9th December, morning at 10:30 a.m. we have fifth session by Mr. V.C. De Silva on topic energy conservation project at Dahanu Thermal Power Station. So I request all participants to join the session. So thank you all of you. So with this I declare the today's session is over.
Thank you,
I
sir.
request
Thank you,
technical
Mr.
team
Sharma,
to
sir.
close the meeting.
Okay, thank you.